congrats, you made it through the hardest math part of the class. Well, you still have the homework to do. But you've made it through. So if you hated the analytical stuff, the good news is now we move to numerical. So if you really like math and you like ODEs and you hate bookkeeping, you're not going to like numerical. But if you're the other way around, you will like it, right? So if all the math has been kind of frustrating, numerical solutions are great because they're easy. Like the concepts are straightforward. So let me give you kind of this comparison. We're going to be developing numerical methods, right? Numerical methods allow you to solve a really wide variety of heat transfer problems, and you can solve problems that you otherwise couldn't solve analytically. So the next couple lectures, we're going to go through like solution techniques that you can use for these. This type of approach is really useful for heat transfer. It's useful for other stuff too. So maybe you've seen it in like some of your other classes. So just drawing some contrast between analytical and numerical. Analytical solutions are exact, right? Under the assumptions that you make. So say extended surface. We assume that there's just a 1D temperature profile. If you make that assumption, you go through the analysis, you get an exact solution according to those assumptions. And that solution is valid everywhere, right? You can plug in whatever value of x, and it'll give you a solution. Numerical solutions are approximate. There's always going to be some error involved in your numerical solution. That error gets better if you use more nodes, more computer power, but it's always an approximate solution. Analytical, very specific. There's kind of limited cases where you can deal with it. Numerical, you can pretty much do any problem that you can come up with. It's very flexible. Analytical requires ODE techniques. Numerical requires algebraic techniques. So we will be going through and developing basically resistance models. Right? You can never get away from the resistance concept. You're going to be developing resistance models that relate heat transfer between nodes. And that's basically the bulk of the technique. The disadvantage of numerical is it's computationally expensive. So to get an accurate solution, usually it requires a lot of computer power. For the problems we're doing, it's really kind of trivial, but like in practice, it becomes expensive. Okay, so let me just talk through really quickly the solution method, and then we'll go through, I guess I have an example, so we'll go through an example, and you'll kind of learn the technique that way. Okay, so there's 5 steps that I've outlined. First step is discretize the domain. So again, we're going to take some conduction problem. This is still conduction. Take that domain and then break it up into a bunch of chunks. All right, you'll discretize the domain into some finite number of control volumes. So this might be like 100 nodes or 10 nodes or something like that. You'll break it up into that number of nodes, and that choice of the number is actually really important, right? We'll have to deal with that. Second, we do an energy balance on each control volume or node. I'll probably call them nodes from here on. That node represents like a single temperature, right? It's like a single point, and that volume is represented by that node's temperature. We represent heat flows into and out of that node using a resistance model. All algebra, right? Remember the equations. It's just a potential divided by some resistance. That's all we're doing, algebra. 4, solve the system of algebraic equations. So this is like implemented in ease, or MATLAB, or Python, or whatever. In this class, we're using ease to solve that system of equations. Step 5, always verify, right? Always verify your solution. So you're going to have like, you're going to go through the 1 through 4 for some problem that you can't solve analytically. And then in step 5, you have to verify it. Well, how do you verify it? Well, you can compare it to an analytical solution in like a limiting case. So say you have like a model, like we'll go through, that has generation that's a function of position or something like that. You can't solve it analytically. But what you could do is you could always go back, change your spatially dependent generation to a uniform generation and solve it that way, and then compare the two. And at least in that case, you can be confident you make like a bad mistake somewhere. Okay, so that's the method. Let's actually go through an example, like I said. All right, so our example, 1D numerical solution, is a non-uniform generation problem. Here we have conduction in one direction, in the x direction, and generation is occurring according to this red curve, where the generation is like increasing near the position th thickness. On the right-hand side of the domain, we have a boundary condition that involves convection, and then there's some depth for this like into the page, which I guess is called W. So let's just go through the steps. Maybe first of all, we could say, if you wanted to solve this analytically, I suppose you could, right? But you're going to have an ODE that involves generation, which is a function of position. And like we did that for that egg problem. It's not necessarily a problem, but it's more complicated. And maybe the form of that function is really weird, or maybe it's a lookup table or something, right? Maybe it's something that you can't actually solve analytically. So we can still do it numerically, right? You don't have to have continuous equations or anything. So let's go through this. So step one is discretize the domain. So what we're going to do is we're going to pick spots where we're going to draw nodes. Let's pick spots like this. So you want to have one node corresponding to each of the boundaries. That makes enforcing the boundary conditions easy. So what I mean is this. So let's first start by drawing a node on the left boundary and drawing a node on the right boundary. We need nodes inside the domain as well. So let's draw equally spaced nodes inside the domain. Right. I'll just pick some in the middle here, and then some on the end. Right. Obviously, you'd have equally spaced all the way through. I'm not just drawing all the dots. So let's discretize the domain and maybe like say, okay, this is node 1, this is node 2, this is node 3. Let's call this node I. This one is I minus 1, I plus 1. And then let's call this node at the end n, and this would be n minus 1. All right. So we've discretized the domain into some finite control volume. So what is the control volume here? I guess the control volume is going to be some box that we draw around the node, right? It's the region that's represented by the node that it corresponds to. So I'm going to draw a box like this. Right? This green line is now our control volume for the ith node. And I've drawn it so maybe it's obvious, but it's halfway between, right? So like they're equal sized all the way through. But that node is right at the center. Okay, so that's the control volume. Let's see, what else can we say? So this distance here is delta x, right? Not dx, is delta x. It's a actual distance, right? It's not a differential length. Delta x, it's some segment or width. What else here? So we have the control volume. I guess we could maybe write equations for this. So delta x, that length is equal to the total thickness. Let's see, what do we have? This here is thickness, right? That's the total length of this domain. So it's thickness divided by the number of divisions or number of control volumes. Well, we have like nodes on the end, so it actually ends up being thickness over n minus 1. Right? That's the number of control volumes that we have. So that's delta x. The node positions, those are going to be x. So x sub I, we're going to index x with the index I. So the ith node is going to be at the position delta x times I minus 1, where, see, I is in the range 1 to n. All right, so I'm creating this set I. So I is an index within the set from 1 to n. This is 1, 2, 3, so on. And I take that value, whichever value of I, plug it in here, and that gives me the position x sub I. Right? One thing you're going to notice here is there's a lot of bookkeeping. If you mess up a problem, it's probably not because the concept is hard, it's because you made a mistake on the index or something like that, or a mistake on the areas involved. So okay, we've discretized the domain. That's fine. The next step is going to be to perform an energy balance on the control volume. To do that, I'm just going to take, so here, perform energy balance on the control volume. So let's identify like the heat flows that are going on here. So we have, it's a little different from our differential control volume analysis. We have potentially heat flowing from across the left boundary. We have heat flowing across the right boundary. In this case, we also have generation. So the one across the left boundary is maybe easy. So let's draw it like this. So let's call this Q dot, I'm going to say Q dot superscript L for node I. Great. Q dot superscript L for node I. That is heat flow from the left-hand side for node I. From the right-hand side, I guess we could draw going out, but it's actually easier to keep track of everything if you just draw everything going in. Right? So we're going to draw everything going in like this. We'll say Q dot R for node I. And the reason why it's easier is because when you do the energy balance for like node I, then you just say like, okay, Q dot L plus Q dot R plus whatever, and it just, you add it all up. In the end, if you're wrong about the direction, it just changes the sign, right? The solution should be the same. Okay, we also have generations, so I'm going to draw here, let's see, what do we have? We know that G dot triple prime times the volume of this node. So I'm going to say it's V sub I, right? It's the volume of the little control volume, not the entire thing. Okay. Any questions on the setup here so far? Yeah.
I just forgot.
Okay. When you remember, you can ask. Any other questions?
Oh yeah.
Yeah.
So why did we choose all of our nodes to be in line with each other and not like varying in the wires?
Yeah, okay. The question was why have all nodes at the center line here and not at different lengths? So the answer is going back to the same like justifications that we've used all along, is that we're only interested in the temperature profile in X for this problem. So the control volume that we use has to cover all, the entire dimension for any other coordinate. Right, so Y. So in this case, we have Y in this direction. We're saying there is no temperature gradient in Y. So I don't need to discretize in Y at all. So I can capture the entire effect of temperature changing by drawing a control volume that covers the entire Y span and is just discretized in X.